Alright, this is my test of doing a video to help you guys understand this chapter. This is for Chapter 4, the Macrostates and Microstates chapter for the week beginning on October 19th, 2008. So there's a few major points to this chapter and I'm going to try to walk through them, and so I'll turn the pages and then I'll get it out of the way and write some notes down. So the first thing is this notion of macrostates versus microstates. Let's take the example of 4 heads of a coin out of 10. Well, let's keep it a little bit smaller. Let's say we have 4 coin flips and we want to know how many different ways you could flip just one heads. Well, you could have heads, tails, 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 and tails, heads, tails, tails, and tails, tails, heads, tails, and tails, 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 heads. So the macrostate here would be the fact that all of these share something in common, and that is that there's 1 heads. There's 4 different ways to do it, so we'd say that's 4 microstates. If you take, for example, rolling dice, if you roll dice, and let's say you're rolling 2 and you're playing the game of craps, and you wanted to know how many different ways you could get, let's say, 7. Well, how many different ways could you do it? Well, there's 1 and 6, and there's 2 and 5, and there's 3 and 4, and 4 and 3, and 5 and 2, and 6 and 1. So there's 1, 2, 3, 4, 5, 6 ways to do that. And so in this case, you would call the macrostate rolling a total of 7. So rolling 7 is the macrostate, and it has 6 microstates. Oops. Writing on the next sheet of paper. It has 6 microstates. And so we can actually understand the game of craps a little bit better because we can understand that rolling 7 is the most popular. How many ways can you roll 11? Well, there's only 2 ways, 6 and 5. So the macrostate here is 11, a total of 11. There's one way to do it, 6 and 5, and 5 and 6. So there's only 2 ways to do it. I'll circle the microstates, the number of microstates, and I'll keep in square what macrostate we're describing. This was describing macrostate 7. So it's clearly more realistic that you're going to roll a 7 instead of 11. Let's try another. How many ways could you roll a 9? Well, there's 3 and 6, 4 and 5, 5 and 4, and 6 and 3. So there's 4 different ways you could roll that. So what you find is that all the casinos, for example, will make it so that they make money if you roll a 7. Because that's going in your direction. I actually don't know the rules of craps, but they certainly can look at these probabilities to figure these sorts of things out. So there's a couple of things going on in this chapter. There's distinguishing macrostates, which is the big thing you're measuring. In the dice case, it would be a total of 7, or a total of 11, or a total of 9, or more generally just the total of the 2 dice. Then there's the microstates, how many different possible ways you could pull that off. The reason we do that is if you consider the air in the room, and so here's a room. Let me just draw a little room here. And we know that we have, a gajillion molecules in here. How many different ways could you put a gajillion molecules in there? Well, you could bunch them all down here in the corner. If you bunched them all down there in the corner, there's not that many ways you can do it, right? You have smaller space, so it'd be harder to find ways to pack them into the corner as opposed to packing them in the whole room. That's why you're not really in danger of suffocation. The chances of all the air moving down to one corner of the room are slim. But I think that hits us to another major point of the chapter. Major point is that all microstates are equally likely. Okay? So it is just as likely for all the air to be in the little tiny corner here in a particular pattern down here than it is to have exactly this molecule here and that molecule there and that molecule there and that molecule there. So if your macrostate is that they're spread out, there's lots of ways to be spread out. If your macrostate is down in a corner, there's a lot less ways for that to happen. Now if all microstates are equally likely, you have to understand, if you go back up to the dice case, we actually think that it is just as improbable to roll a 6 and then another 6 as it is to roll a 3 and then a 4. Each of those are equally unlikely. The thing is that 6 and 6 is a lonely microstate. There is no other roll you can get that gives you a total of 12. 3 and 4 is not lonely. If you look up here, 3 and 4 is just like 4 and 3, it's just like 5 and 2, it's just like 6 and 1. It's not a lonely microstate. But each individual microstate alone, that one or that one or this one or this one, they're all as likely because all microstates are equally likely. That is a very, very important point that we're considering here. Remember that our goal is to figure out how the heck things are irreversible. And in fact, the answer, as I believe was mentioned in the discussion board, the answer is a probability issue. Next, we want to talk about this Einstein Solid, this notion of springs holding everything together. I think that this image right here, which I'm going to just display upside down so that the camera it doesn't get in the way, this image here is something that we all teach. Molecules are held together by springs. What we are doing is, for the Einstein Solid, is we're saying specifically that there are 3 ways that each individual molecule can move. It can move left and right, up and down, and in and out of the page. When it moves left and right, we're not saying there's 3 springs for every particle. You can see that each particle is connected to 1, 2, 3, 4, into the page 5, out of the page 6. So each particle is connected to 6 springs. But if we talk about its degree of freedom in the horizontal direction, these 2 springs work together. In fact, their spring constants work together to get the effective spring constant in the horizontal direction. There's an effective spring constant in the vertical direction, and a spring constant, an effective spring constant out of the page. And so if we want to write down the energy of a solid, we have to say, well, the energy of a solid is going to equal the sum of the energy of each particle. Okay? The simplification that's happening here is that this is really going to be the sum of 3 springs, spring-like terms, for each particle. Sort of put that in parentheses. Now here we get a little bit of quantum that we haven't really studied, but I think people don't really have a big problem with this. Certainly we know that in the Bohr atom, you can be here or you can be here. Well, it turns out that for a spring, which is just a particular way to bind things, we know that for a spring you have a parabolic potential energy. If I call this U potential energy and I call this position, we normally think that, you know, something could go back and forth any height you want. You could drop the ball from here back and forth, or from here back and forth, back and forth. What we learn in quantum mechanics is no, it can be this high, or this high, or this high, or this high, but not there. It can't be that height there. Now we're going to learn a lot about that next semester in the online quantum course. For now, that's really all we need, is that if you have a bunch of spring terms, every single one of them is going to look like, well, either this much energy, or this much energy, or this much energy, or this much energy. What's really nice about spring terms is that these spacings here, all of these spacings are identical. So these all are the same size. That's why this math in this chapter is a lot easier than it would be for other types of systems. So we say that if we have this sum for 3 spring terms, that now becomes a sum from I equals 1 to 3 times the number of particles. Why 3 times the number of particles? It's 3 times the number of particles because each particle has 3 spring terms. Now, what does this energy look like? Well, it's some spacing, the same size is going to be called epsilon, times an integer, n sub I. Now there's this extra plus 1/2. That is only because the very first spacing, this one right here, is half of epsilon. Now, we just live with that. We're going to learn a tiny bit about that next semester. We just have to accept that. But of course our author points out that that contribution to the sum never changes. In fact, he shows us that this ends up being, and by the way, this is equation T 4.4 on page 63. We show that this sum becomes a sum I equals 1 to 3n of epsilon times n sub I. What is n sub I? That's just an integer. You can either be here or here or here. Let's just count them up. Let's call this the 0, this the 1, this the 2. Label them 0, 1, 2, 3. So that's what these integers are. Every single spring can be in an arbitrary one of these. But now they all can't be super high. They can't all be up here if your system doesn't have enough energy to do that. If your system on average has, if each particle has roughly this much energy right in the middle, we know the particle can't have that much energy, so that means a lot are here and a lot are here so that the average works out. Now I'm not done with this here. This is plus an additional 3/2 total number of particles times epsilon. Author points out that, what does he call that? He calls that the 0-point energy. Remember, that's never going to change. No matter what you do, that's your ground state energy. If all of your n's are 0, you're going to have that much energy. But keep in mind that only energy changes matter in physics, in our universe. If that's never going to change, we are effectively going to ignore it. And so we get a relatively simple expression. So, if you know what epsilon is from now on, maybe I'll just go ahead and say that epsilon equals 1 to make my life easier. If epsilon equals 1, then the total energy that seems to matter, the total energy that has a chance of changing, is going to be the sum, I equals 1 to the 3 times the number of n, again, number of particles. Each particle has 3 springs because of the 3 dimensions that it's in. And if epsilon equals 1, I just get n sub I. And again, these are integers. Those are integers. So, how many n sub i's are there? 3n of them. 3 times n integers will completely describe the system. So a microstate, in this case, a microstate could be, let's say I have 2 particles. How many springs do I have? 2 times 3 is 6, so that's 6 springs. That means I have 6 integers. Alright, well, how many different ways you could do that? Well, I could have 0, 0, 0, 0, 0, 0, or I could have 17, 147,000, I'll put bars here, 7.6 times 10 to the 12th, 0, 14, 1, 2, 3, 4, 5, and 63. As long as they're integers, they're fine. Note that this one is an integer, okay? Now, so they're all equally likely, but you have to make sure that you have enough energy to accommodate it. So it's not enough to say for the macrostate how many particles you have. Certainly that tells you all of this information. I'm just going to make sure I'm still in focus here. Reasonably in focus. I certainly have this information, but I also need to know the total energy. Total energy, I'll call it U sub t. And if I say that U sub t in this case is 4, then I'm severely limited, right? I can have 0, 0, 0, 0, 0, 4, or I could have 1, 1, 1, 0, 1, 0, or I could have 2, 0, 1, 0, 1, 0. There's a few ways to do it. And certainly your book gives you all kinds of equations for counting that. But let's just take these 3. If we think, and I'll grab my little sheet of paper here, if we think that all microstates are equally likely, then it is just as likely that your system is in this, as in this, as in this. So, how many different ways could just one particle, one spring, hog all the energies? Well, there's one way. You could put it in this one, 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 this one, or this one. There's 6 different ways that all of the energy would be hogged by one person. It turns out that that's, okay, so there's 6 microstates. I'm going to write this has equals 6 microstates. But how many ways could it be evenly spread? Well, let's see here. This is tough. I could go, let's see if we can write them down. So I want it to be equally spread. So 4 with 1s and 2 with 0s. Let's see if I can write it down. It's going to be 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, and there's probably a few more. Certainly more than 6 though. 1, 2, 3, 4, 5, 6, 7, 8. I've already found 9 ways to do it. So the microstate, let's call this microstate communism has more. I'm sorry. I apologize. This is a macrostate because it's a big thing. Macrostate is communism, evenly spread. We found that there's at least 9 ways to do that, whereas there was only 6 ways of, let's call this, I don't know, capitalism or something. Just kidding. There's only 6 ways to do capitalism. There's at least 9 ways to do communism. So you're going to see more communism than you are going to see capitalism in this case. The whole point of this chapter and the next few chapters is carefully calculating this kind of thing. All right, so let's move on to putting... I'm sorry, let me also point out that T.4.7, the equation on page 65, is a way of calculating these things. So let's take a look at it. T4.7 is the number of microstates for a particular number of particles. So keep in mind that means that there's 3 times n springs and a total amount of energy. This is the total energy. Really, another way to think of that is Q, because Q is the total energy divided by epsilon, so that's how you can get everything into integers. And it's just some simple, well, relatively straightforward math. 3n minus 1 factorial over Q factorial times 3n minus 1 factorial. Okay? So let's go back and check the thing that I was trying to figure out. All right? So, let's see. Let's find out how many microstates you would have if all you knew, if the macrostate was that you had 4 units of energy spread over 6 springs. How would you do that? Well, 6 springs we know is 2 particles, so we would have Q equals 4, n equals 2. So we would have 4 plus 3 times n is 6 minus 1 quantity factorial over, I don't know if you can see, so I'm pushing this up. Q factorial is 4 factorial times 6 minus 1 factorial. So this ends up being 9 factorial over 4 factorial times 5 factorial. I don't have a calculator handy, but I have a suspicion this one has worked out for us. Let's see here, 4 units of energy, 126. There we go. I actually got that from problem T4S.2. T4S.2. So that's how to do those calculations. The point is here we're just doing basic counting. All right. Let's ask the question, what about 2 systems? Let's have system A and system B in contact with each other. I purposely drew B bigger. Don't be alarmed. B is bigger. Okay? Maybe it has more particles. Okay? So it's got the number of particles in B and the number of particles in A. Okay? We know macroscopically that if one of them starts hot and the other starts cold, the heat will flow from the hot one and go to the cold one. We know that that doesn't violate conservation of energy, but frankly, what if heat had been drawn from the cold one to make the hotter one hotter? Turns out that doesn't violate conservation of energy either. We're trying to understand why it only ever flows one way. This chapter is setting us up. Next chapter and the chapter after that helps us understand it. All right, so what are we going to do here? Well, let's say I want to dump into this energy, into the system, a total energy of U total. Okay, so U total is going to be sort of dumped in to the system somehow. You can do it lots of ways. Spread it out evenly, give it all to A, give it all to B. No matter how you do it, eventually, we think anyways, that it's going to be spread out. We want to try to understand that. Well, at any point in time, A is going to have some energy, B is going to have some energy, so it's very important to understand that the sum of their energy is fixed. This equation is fantastically important when using the computer program that this chapter talks about, because the computer program only ever gives you this information and this information. You have to understand that if you ever want the other one, you just have to say, well, for example, UB equals UT minus UA. That way you get them both. So just keep that in mind. So we're going to give a total amount of energy to the system. We know that at various times A is going to have some energy, B is going to have some energy, but they're not arbitrary. They have to add up to the total energy. So if, just looking ahead to problem, well, I don't know what it is, TS.4, if you put two systems together, let's see, so in that case, well, I don't want to give too much away. Maybe we'll just do a fake system or something like this, okay? In fact, let's just look at table 4.1. So table 4.1 looks like so. Just going to make sure the camera's got it good. Oh, it doesn't really. Ugh. Let me zoom on it. Zoom away. Okay, so here we have a table of a system of just one molecule each. That means that both systems have 3 springs. We're just going to give it 6 units of energy. How many different ways can you do that? Well, if you could give all the energy to use of B, or you could give all the energy to A, and everything in between. As soon as you know what A has, you know immediately what B has. Has to work that way. Now, turns out, how many ways could you give A 0 energy? Well, you can give 0 to the first spring, 0 to the second spring, and 0 to the third spring. There's only one way to do it. How many ways could you give it 3 units of energy? Apparently there's 10 ways to do it. So in probability, if you're asking for 2 things, like, for example, the chance of flipping 2 coins in a row, you multiply the probability of ways that it can happen. That's why we're multiplying these multiplicities. That sounds funny. So we want to know the total ways that you could have 2 units of energy in A and 4 units in B. Well, A has 6 ways to do it. B has 15 ways to do it. Let me draw that schematically for you. If you think 1, 2, 3, 4, 5, 6 ways of doing it for A, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 ways of doing it for B, it could be like that, or 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 it could be like that, right? You'd have to grab one from the top and one from the bottom. How many different ways is it? Well, it's going to be 6 times 15, which I believe is 75. I can't do my own math. 90 apparently. looking back at this. Sorry, I forgot that I'd zoomed in. Let me move it over. Looking back at this, we see, sure enough, 90 ways that you could do that. Now, this now is an interesting statement. It says, to have all of the energy in B, there's 28 ways to do it. To have it evenly spread, there's 100 ways to do it. Now remember that all of these 462 microstates, all of them, are equally likely. But it seems like there's more of them grouped together when you spread the wealth than when you hog it. So in this chapter, we want to do that over and over and over again. I'm going to zoom out again. Darn it. I see that I didn't zoom properly before. I apologize about that. So, what are we going to do about this? Well, you need to use the program. That's just all there is to it. And the program kind of looks like this. It's a nice little window. Okay, you put in what NA is, you put in what NB is, you put in what the total energy is. Here you choose 1,000, it's the max number of rows. Just leave it at 1,000 unless having gobs of rows bothers you. Okay, then there's this cutesy little calculate button, and there's table choice or graph choice. Okay, whenever you do it, you go ka-chung, you hit that. You can put any number you want, here, here, and here, and then hit calculate. You will get a table just like table 4.1. Okay? So let's say you wanted to know, well, my gosh, what if I had 50 molecules connected to a system with 100 molecules? Just do it. Plug it in. And let's say you wanted to give that system just 1 unit of energy. Well, you can find out all the different ways that you can do that. And so the homework problems in this chapter should set you up to be able to do that. I think I'm going to stop right there for this initial test with this, and we'll see how it goes. Please give me some comments online.